Hello and welcome back to Comp 3430 in my messy basement office. We're done week 4. That means that we are technically two-thirds finished this course already. This feels like an unstoppable locomotive at this point. Feels like we're just moving fast and we're getting through the course. Let's take a look at where we're at in terms of the topics that we've been looking at and start to think a little bit about, take a look at some of the learning outcomes that we've got for the last couple of weeks. So let's take a look at where we are in the course right now. Last week we were in week 3 and our topics last week were scheduling. Last week was kind of truncated because we had a term test and because we had a holiday on Monday. And the only topic that we really talked about was scheduling last week. The other half of that, IO scheduling, and physical representation, we have talked a little bit about that, and I'll look at these learning outcomes in just a second, but we haven't spent a lot of time in class talking about these yet. This week, we focused primarily on file system implementation, and the goal here was basically to get you set up for working on Lab 3 and Assignment 3, which is implementing code and writing code that's dealing with exFAT, a file system that's designed by Microsoft. We also didn't get to file systems consistency and redundancy because we were spending a little bit of time on Monday's class talking about the Lab 2 and Assignment 2. And then we got to file systems and that just took a little bit longer than expected, and that's okay. So let's go down and we'll take a look at the learning outcomes for IO scheduling. So in part 2 of week 3, this is where we were last week. We've got a few different learning outcomes here. Describe how an operating system communicates with hardware devices. This is coming from chapter 36 in the video. And again, with the videos, you can pick either reading the chapter or watching the video. You don't have to do both for the ones where there are videos. Describe how an operating system communicates with hardware devices. What I'm really looking for here is related to this other learning outcome. Explain how an operating system provides an abstraction around hardware devices. This is both going to be the idea of device drivers and the idea of how hardware is communicated with in terms of like reading and writing registers, so memory mapped IO, or instructions, specific instructions that are given. So x86 has like input and output instructions for reading and writing from a drive. Compare and contrast methods for improving performance of communication between operating systems and hardware devices. This is fundamentally the idea of DMA. So having our devices directly attached to the system and then be able to directly write to memory. These 3 learning outcomes describe how an operating system communicates with hardware devices, compare and contrast methods for improving performance, communication between operating systems and hardware devices, explain how an operating system provides an abstraction around hardware devices. These are learning outcomes that will be assessed on a final exam. You're not being assessed on this in any way on assignments or labs, and this is entirely going to be on a final exam. Describe the physical structure of a hard drive. This one we did actually talk about in class in addition to chapter 37. And this was the day that I brought some drives for show and tell and gave you an opportunity to take a look at an actual drive. This was the idea of tracks, sectors, cylinders, surfaces, platters, and so on. This is something that could be assessed on a final exam, although this is mostly just define terms, really just define terms, and I'm not really that interested in assessing you on that. This is something that you could just memorize. You're implicitly being assessed on this in terms of implementing a file system reader. So you have to go through the process of translating between sectors and clusters or sectors and blocks. So you're implicitly being assessed on this. Given a disk layout, describe what happens as an IO request for a block or file is serviced. compare and contrast IO scheduling policies and process scheduling policies. Compare and contrast IO scheduling policies. Given a disk layout, describe what happens as an IO request for a block is serviced. This learning outcome comes from chapter 37. I think that I am going to strike this learning outcome from the course just to reduce the number of things that we're being assessed on. Compare and contrast IO scheduling policies and process scheduling policies. I'd like to come back to this. So this is coming from chapter 37, where it describes things like scan and cscan, and then basically as the disk heads are moving across the platters and the surfaces, how do we decide which IO requests go first? How do we make that decision? We'll talk a little bit about this in class, but this is coming back to chapter 7, 8, and 9, and going back to scheduling processes and starting to think about some of the unrealistic assumptions that our authors gave us about scheduling processes. Compare and contrast IO scheduling policies. Again, this is coming from chapter 37, and both of these are going to be something that could be assessed on a final exam. This is not something that you would have assessed in an assignment or lab in any way. So of these ones, given a disk layout, describe what happens as an IO request is serviced. This is going to be stricken. This will not be part of the course. The other parts are things that could be assessed on the final exam. For this week, what we were doing was taking a look mostly at file systems implementation. We've got just a few learning outcomes here in the first part. Describe the data structures used to represent files and directories as seen in Unix. This is really directly saying, tell me that you understand the idea of inodes and how inodes represent files and how directories are represented in terms of an inode for a directory points at a block that's filled with directory entries, file names, and inodes. And sort of the idea that an inode doesn't have a file name, but rather the name is given by the directory that the inode is contained within. There's kind of this weird switch between how how an inode doesn't actually have a name, it just has a value and like points at a block or blocks on the file system, and the names are given by their presence in a directory. This is both discussed in chapter 39 in the form of like you've got your file explorer and this is what files and directories look like, and here are some of the APIs that you can use to interact with files and directories, but this is more directly described in chapter 40, the file system implementation. So this is either the video or chapter 40. Show how common file operations are performed in terms of manipulating a file system's data structures. So this is related to the last one. What are the data structures? And now if we start to talk about system calls, what are the system calls that can make changes to data structures? Which data structures are changed and how are those data structures changed? So if, for example, I am doing an open for create, which data structures in a file system are modified and updated and so on? This comes from chapter 39 and 40. Again, more chapter 40 than 39. Chapter 39 is talking about the API. Chapter 40 is talking about the actual data structures. Both of these are related. This is going to be something that you can expect to be assessed on in something like a final exam. This is not something that you are being assessed on in your assignment. We're not modifying any of a file system's data structures in lab 3 or assignment 3. We're only reading them. So that's not what this learning outcome is being. This learning outcome here is not being assessed in the lab or the assignment because we're not actually making any changes to a file system. Explain how files are managed as part of a process's active state. So this actually goes back to week 3 and chapter 5, thinking about things like the open file table in a process control block, and how when we are doing things like opening a file, so how common file operations are performed in terms of manipulating a file system's data structures, how does the operating system maintain a process's state? So we're making changes to the open file table while we're also making changes to the inode table or the data map, the data bit map in a file system. Again, this is going to be something that you could expect to see on a final exam. This is not part of the assignment or the lab. Describe how a specific file system is implemented. At this point, you've seen two different file systems. exFAT, this was done entirely in class, and VSFS, this was done both in class and it's done in chapter 40 and in the video. And there's a lot of overlap between the material that we had in class and what's in chapter 40 and what's in the video. This is something that you could expect to see on a final exam. This is probably going to be more of the form of tell me a little bit about how the file system is implemented and then do some assessment of the file system. The last learning outcome, write code to read a file system. This is definitely going to be part of an assignment in a lab. This is where you're going to be assessed on lab 3 and assignment 3. This kind of goes back all the way to lab 1 and assignment 1, where at least in lab 1 specifically, you were asked to read a binary file. You're going to continue to read a binary file in lab 3 and assignment 3, except the binary file's format is exFAT. It's not Windows COFF or PE formatted files, and it's not an L formatted file. It is a file system. It's a binary file that has a file system. We're going to get to file system consistency and redundancy next week. So we're falling a little bit behind schedule, but that's okay. If there's stuff that falls off the end of the course, I'm okay with that, and I will tell you explicitly if something has fallen off the end of the course and will not be on the final exam. But to give you a preview of what we're going to be looking at next week at the beginning, file systems consistency and redundancy, the two big things that we're going to be looking at in terms of consistency and redundancy is RAID. So you need to know a little bit about what the RAID levels are, and what we're going to have a discussion about is once you have requirements, so kind of like scheduling, kind of like choosing a file system, given a workload, what you want to accomplish, which RAID level is the right RAID level. The other thing that we're really going to be looking at is describe what a human operator might see in files when a file system is in an inconsistent state, and identify inconsistencies in a file system. Identify inconsistencies in a file system, you are actually going to be assessed on this one in lab 3. There's not like a lot to talk about here. We don't have to spend a huge amount of time discussing what identifying inconsistencies in a file system are, other than to say that we've got data structures in the file system that don't agree with each other about what's the truth. So one place that you're going to be looking at in lab 3 is with exFAT, we have an allocation structure, so similar to the data bitmap in VSFS. We can count how many clusters are free and thus how much space is used in the drive. But the master boot, the main boot sector has a property called percent in use, and these two things may not agree. Identifying inconsistencies in a file system, you're being assessed on this one in lab 3. Describe what a human operator might see in files when a file system is in an inconsistent state. You're definitely going to be assessed on this on something like a final exam. Repair an inconsistent file system. We're not going to do this. We're not going to do this in lab 3. You're identifying inconsistencies in a file system in lab 3. You're not actually making changes to the file system to correct those errors. This is related to this one. So describe what a human operator might see, repair an inconsistent file system. So given an inconsistency, what's the appropriate choice to make for how to repair that file system? Describe strategies for repairing or preventing inconsistent file systems. Compare and contrast strategies for repairing or preventing inconsistent file systems. Compare and contrast traditional file systems with modern approaches such as log structured and journaling file systems. This is all journaling. This is chapter 40, 42. So chapter 40 is back up here in the previous week. Chapter 42 here is file system checking and journaling. This is kind of going through the process of saying, how do we repair or prevent inconsistent file systems? So file system check or journal, and then compare and contrast traditional file systems with modern approaches such as journaling file systems specifically. We're not talking about log structured, we're only going to be talking about journaling file systems. And what I'd be looking for you to do here is tell me about some of the differences that you might expect in between something like exFAT, which doesn't have a journal, and a file system that does have a journal. So be able to define the term journal, but tell me about what the effect of having that journal will be. That's where I'm going to stop with this video because we're kind of in this state right now. We just finished this file system implementation, and we're going to be going to file system consistency and redundancy next week. Later in the week, we're going to be taking a look at virtual memory and virtual memory and memory segmentation specifically. I really love this memory segmentation part of the course because we finally get to find out what segmentation fault actually means. This is something that you see so much when you're writing C code. To finally be able to find out what that actually means and to find out that it's a complete and utter lie on modern systems, I think is great. So I'm looking forward to being able to have that discussion with you. All right, so that's where we are this week. That's kind of how you can expect to be assessed on some of the learning outcomes that are in the course schedule right now. And like I said, if stuff starts to fall off the end of the course, that's okay. I will let you know in advance if stuff is falling off the end of the course so that you don't have to spend time preparing for that stuff in the final exam when you're preparing for the final exam. That's it for today. I hope you have a great weekend, and I'll see you all on Monday. Bye.